Welcome back. In this section, we're going to cover experiments and observational studies. This is section 1.3 from the textbook. And there's a list of 5 things that we're going to want to look at. The number one is association versus causation. How are these related to each other? How are they different from each other? Observational studies versus controlled experiments. It's very important that we understand the difference between these types of studies. Placebos and blinding, types of experiments, and finally, and very importantly, the 2 different ways in which randomness gets used in this context, okay? So let's begin with understanding the difference between association and causation. Okay, 2 variables are said to be associated if the values of one variable tend to be related to the values of the other variable. On the other hand, 2 variables are causally associated or simply causally related if actively changing the value of one variable influences the value of the other variable. So there's a notion of actively changing one of the variables that's very important in distinguishing causation from mere association. Now, we're going to look at some examples, and hopefully by the time we're done with that, we'll understand better how causation and association are alike like each other and how they're actually very different from each other. Okay. Now, when we're talking about association, we can also talk about a direction of association. So the direction is considered positive in this example. As the restaurant bill goes up, the size of the tip goes up. And as the restaurant bill goes down, the size of the tip goes down. So we can kind of see that there's an association between the size of the restaurant bill and the size of the tip. And in this case, we would say the direction is positive because they increase and decrease sympathetically. Okay. There's also a notion of a negative direction. So for example, as the outside temperature goes up, my heating bill goes down. And as the outside temperature goes down, my heating bill goes up. Here we can kind of see the negative association. As one of the variables is going up, the other one is going down, and vice versa. So association just means that these variables are connected to each other. That connection could be positive or negative. All right. Let's take a look at this problem. All right. It has been widely observed that as ice cream sales go up, so do the number of shark attacks. And as ice cream sales go down, so do the number of shark attacks. So our ice cream sales, which we'll denote by the variable I, and the number of shark attacks, which we'll denote by N, are I and N likely associated with each other? And here we would say yes, because we're noticing time and again that as the sales of ice creams go up, the number of shark attacks go up, and as ice cream sales go down, the number of shark attacks go down. So we would recognize this as a valid positive association. Now, let's take a look at these follow-up questions, though. Does I cause N? Does I cause N? Now, remember, to distinguish between mere association and causation, we now have to play the following game. We have to ask ourselves, if I influence, if I'm able to actively change the variable I, am I going to see a corresponding change in the variable N? So in asking, does I cause N, I'm asking myself, if I actively control the sale of ice cream, is that going to have a sympathetic change in the number of shark attacks? And if we think about it this way, we see how silly this is, right? If we go into Myrtle Beach, South Carolina, and I force more ice cream sales in the winter, or I decrease the number of ice cream sales in the summer, I don't expect to see a change in the shark attacks. I'm really not expecting that. So in this way, we can see that even though these variables are linked in an association, and in fact a positive association, we don't believe that I causes N. Now, let's reverse the roles. Do we believe that N causes I? Now I would have to actively change the number of shark attacks and see if there's a response in the ice cream sales. And here again, we think that this is ridiculous, right? So imagine that I go out into the waters with a group of very brave volunteers and I chum the waters and I try to induce a greater number of shark attacks, do I believe that on shore there's going to be an increase in the sales of ice cream? It's ridiculous, right? So we don't really believe that N causes I either. So I does not cause N does not cause I. We just believe that there's a mere association between them, a positive association in this case, but not a causal relationship, right? So what is going on here, though? How is it possible that we can have associations without either variable causing the other? Oftentimes, we can explain this through what's called a confounding variable or a lurking variable or a confounding factor. So let's take a look at this definition. A confounding variable, also known as a confounding factor or as a lurking variable, is a third variable that is associated with both the explanatory variable and the response variable. So a confounding variable can offer a plausible explanation for an association between two variables of interest. Now, in the example we're looking at ice cream sales and shark attacks. We've examined the causal relationship, and we see that there is no causal relationship. We don't believe changing ice cream sales affects shark attacks. We don't believe actively changing the number of shark attacks is going to affect ice cream sales. Nonetheless, we believe that there is a valid association. So we might start asking ourselves, what's a plausible lurking variable that is influencing both of these simultaneously? And if we think about it, it's the weather, right? It's the time of year, it's the seasons. We know that ice cream sales will go up when the weather is warm, and we know that when the weather is warm, it brings different currents inshore. There's more people in the water, and the people are coming in contact with sharks in that warmer weather. Likewise, as we move into the fall and winter, people are not swimming, the sharks are moving offshore, and ice cream sales are going down because people are frankly not that interested in eating ice cream as the weather gets colder. So what we see here is the presence of a third or a lurking variable, a hidden variable, which is causing an association between two other variables. And so looking for these confounding variables is often an important exercise in understanding an association. All right, let's take a look at another example of this before we leave this topic. Bill is single. He has just read a study claiming that on average, married men live longer and earn more money than single men. He wonders, I want to live longer and earn more money. Should I get married? Comment on this. Now, I'll let you pause the video and think about this scenario and ask yourself, does Bill have this right? Is he thinking correctly about this situation? So, if we think about this together, let's see what he's doing. He's actually making a causal relationship between the variables married or not married, so that's a categorical variable, and living longer and earning more money. He's saying that there's a causal relationship, that the act of getting married will change my life expectancy and my earning potential. Now, the study is actually not claiming this. The study is just drawing an association between these. It's noticing that married men, right, tend to live longer and earn more money, but it's not saying that that's the cause of the relationship. So Bill is actually not thinking about this correctly. He's not saying something that the study, he's not using something that the study is actually claiming. In fact, there is some evidence that if there is a causal relationship at all, it might be in the opposite direction, that the causation may run in the opposite direction. In other words, one way to think about this is that the health that you project and the earning potential that you project are things that make you attractive to a future spouse. So, in fact, Bill is not thinking about this correctly. In fact, the causation, if there is any, is probably going in the other direction. So this does not make much sense for Bill to think this way. All right, now we're going to move on to our next topic, and that's to take a look at observational studies versus controlled experiments. Okay, observational studies versus controlled experiments. So that's up next. Let's take a look at these two definitions in some detail here. We want to compare and contrast controlled experiments with observational studies. So, an experiment is a study in which the researcher actively controls one or more of the explanatory variables. By contrast, an observational study is a study in which the researcher does not actively control the value of any variable, but simply observes the values as they naturally exist. Now, it's really important to put fences around these two ideas to keep them separated from each other. And anytime you're reading a study, to ask yourself, am I looking at a controlled experiment or am I looking at an observational study? And one important reason to draw this distinction is that when you're looking at an observational study, since you're not controlling the explanatory variable, you will never be able to assert causality from a mere observational study. Now, observational studies are tremendously important, and in some sense, in some circumstances, they're the only thing we can do ethically, but you'll never be able to really draw causality out of an observational study because you have failed to control and change the explanatory variables. In a controlled experiment, since you have control and since you can actively adjust the explanatory variable, you can, right, if it's done carefully, assert causality between the variables. So let's take a look at some examples to see if we can flesh out this difference. So, setting aside for the moment all ethical considerations, design an experiment to test the effects of sleep on grades in children. How would ethical considerations change our experiment? What could we do instead? What might be lost in the exchange? So first of all, we want to imagine that we're not bound by any ethical considerations, that we can actively control how much sleep children get at night, and then we can look at their grades as a response. And then we can ask ourselves, since that seems somewhat unethical, what could we do instead? But what would we lose in exchange for conducting this experiment differently? All right, so here's what we might do if we try to treat this as a controlled experiment. The first thing we would have to do is get a subset of children that we think really represents the population of grade school children as a whole. So we first want to assemble a group of volunteers. We want to make sure that they are representative, so we want to draw them somewhat randomly from the population of all school-aged children. And then what we want to do is we want to decide ahead of time on how many different levels of sleep we want to examine, because sleep is going to be our explanatory variable, and grades or grade point average will be our response to that. And so we have to actively control the level of sleep that we're going to allow these children to have. So we'll have to decide ahead of time how many different categories of this explanatory variable are we going to put the children into. So maybe we decide that some of these kids will get 6 hours of sleep, some will get 7, some will get 8, and some will get 9. And then what we have to do is we have to take our group of children and we have to randomly allocate them to these groups. All right. Now, why are we randomly allocating the children to these groups? Well, we're acknowledging ahead of time that there might be lots and lots of different variables that go into a child's grade point average. We think that sleep is one of them, but not the only one. And so by randomly assigning the children to these various sleep groups, we're acknowledging that we're trying to wash out any other effects that there might be, that we're not purposely putting all of the young girls into the 6-hour sleep group and then the boys into the 9-hour sleep group, because we know that maybe one of the factors in grade point average in grade school children might be the gender of the child, for instance. So we want to just make sure that we're washing out any other possible explanations for grade point average by randomly assigning these kids to these groups. But we might want to use a tool like random.org to take these children and color them black, blue, red, or green to put them into these different sleep groups. And then what we're going to do is maybe for an entire quarter, we're going to make sure that their parents allow these kids only 6 hours of sleep, these kids 7 hours of sleep, etc. And then we keep track of how they do in terms of their GPA. What kind of response do we get? Now, if it does turn out that there is an association between sleep and grade point average, because we've actively controlled the explanatory variable and we've seen a sympathetic response and association with the explanatory variable, here we could begin to validate the conclusion that sleep, right, causes an effect in the grade point average. Okay? Now, there are ethical considerations here, right? Is it fair, right? Is it ethical to deprive children of sleep? Because sleep is very, very good for their growing brains. And so there might be ethical questions about whether we can limit a child's sleep to 6 hours. So what we may be forced to do instead is to merely treat this as an observational study. We'll just have the parents report at the end of the quarter what the average sleep per night was for each child. We can put that together with their GPA, and we can just look at this as an observational study where we didn't control how much sleep the child got. We merely observed it. And we might see an association between the amount of sleep per night and their GPA, but we would now no longer be able to assert a causal relationship between these variables. Okay? That would be lost to us if we treated this as a mere observational study. Now, that may be the best that we can do, and there's some valid information contained in that, but we do lose the effect of causality here. Okay. Now, one last thing that I want to do is look at a randomized experiment, right? In a randomized experiment, the value of the explanatory variable for each unit is determined randomly before the response variable is measured. If a randomized experiment yields an association between the two variables, we can establish a causal relationship from the explanatory to the response variable. This was our consideration in conducting our experiment, to take our group of volunteers and randomly place them into our 4 different sleep groups, right? We're trying to wash out any other possible effects on grade point average by doing that, and trying to just find a relationship between the one variable of interest to us, the one explanatory variable, which is sleep, and the response variable, which is grade point average. Okay, so that's part of randomizing this experiment. Okay, so that brings an end to this subsection on observational studies versus controlled experiments. And hopefully by looking at this sleep study, we can see that these 2 experiments are conducted rather differently, and the kind of conclusions that we can draw out of these experiments are dramatically different. Understand, though, that in many, many situations, the best thing that we can do is an observational study. And this is often due to ethical considerations. So that's often the best we can do, and it's better than nothing. It's just not as strong as a controlled experiment. Okay, now the next thing we're going to want to study is placebos and blinding. One way to understand placebos and blinding is to look at it in the context of an example. Can megadoses of vitamin C prevent colds? We want to design an experiment to study and answer this question. So we need to understand 2 things about human nature, though. All right. Number 1, the mere act of taking a pill will make some people feel better. All right. And number 2, the investigator has an active interest in the outcome of this experiment. Perhaps he or she desperately wants to show that taking these megadoses of vitamin C is good at preventing colds, right? That's the answer they want. So we have to understand that the investigator will be actively interested in the outcome of this experiment. They are not a disinterested party, and they may be inclined to fudge the data. All right. So knowing these 2 things about human nature, what kind of things can we build into our experiment to help us overcome these things? All right. So here's one way we can think about this. It's not that different from the study that we looked at earlier. We're going to create, let's say, 4 different dosage levels of vitamin C because we want to actively control the level of vitamin C. We want to be able to look at it in different levels of dosage, from dosage 1 up through, let's say, dosage 4. We also want to take our randomly sampled group of volunteers from the population. So we hope that these people represent the population as a whole. And we want to randomly assign them to these different groups. So we want to put some people in the black, blue, red, and green group randomly. Again, because there might be lots of things that affect whether or not you get a cold during our testing period. And so we want to wash out all of these effects by randomization and concentrate just on the effect then in our experiment of the vitamin C dosage. Now, The placebo effect, as it's called, the idea of taking a sugar, the idea of just the mere act of taking a pill might make you feel better. To counteract that, what we're going to always do in our experiment like this is make sure that one of these dosages, let's say dosage 1, is a nothing dosage. There's no vitamin C being communicated at all. In fact, these patients are just taking a sugar pill. Now, the placebo effect also works in this way too, right? That as they're receiving these different levels of dosage, the people that are receiving, for instance, this highest level of vitamin C may feel like superhumans, right? And so this may induce a psychosomatic response in them. So we also want to make sure that these people don't know which dosage group they're in. We want to blind them to which dosage group we're in. So all they're going to know is that they're in some group, they're getting some dose of vitamin C, but we're not going to tell them whether it's a lot or a little. We want to blind them to which group they're in. Okay, now, remember that the investigator has a vested interest in this answer. And one way to overcome that tendency to fudge the data or to skew the data, to misinterpret the data, is to blind the investigator as to which group the participants are in as well. So the investigator will have no knowledge when he's interviewing these people which group they're in. He or she is conducting this experiment blind to which group the people are coming from as well. And so this would be what's called a classic double-blind experiment, where the people have no knowledge of which dosage group they're going into, and the investigator has no knowledge of which dosage group the participants are coming from. And we're also overcoming the placebo effect by having a control group D1 here, let's say, that is not giving this participant any vitamin C at all. All right. So if at the end of this experiment, we see that there's an association between this input variable, the explanatory variable, which is vitamin C dosages, and this response variable of the number of colds that were witnessed during the testing period, then we can start to infer causality from this. Okay? So, the placebo effect. If people believe they are getting an effective treatment, they may experience the desired effect regardless of whether the treatment is any good. This phenomenon is called the placebo effect. So one way to overcome that is to create a null group, a group that is not getting any of the treatment, and let them believe that they're getting something. Okay? Blinding. In a classic single-blind experiment, the participants are not told which group they are in. So this is also preventing some kind of further consequences of a placebo effect. We won't let them know that they're getting the more effective or less effective dose of vitamin C, and we will prevent them from having some kind of response just from knowing what group they're in. In a classic double-blind experiment, the participants are not told which group they're in, and the people interacting with the participants, the investigators, and the people who are recording the results of the response variable also do not know who is in which group. So that's kind of the classic double-blind experiment. Okay, so as we close this section on placebos and blinding, just remember that when we're conducting these experiments, we have to build in to these experiments the knowledge that we're working with human subjects who are subject to the placebo effect, and we're working with investigators that are subject to having a vested interest in the answer coming out a certain way. So we have to build in precautions in working with human subjects. All right, our next topic is going to be different types of experiments. Okay, we really want to make a distinction between two different types of randomized experiments. So, in a randomized comparative experiment, we randomly assign cases to different treatment groups and then compare results on the response variable. So, this is the kind of experiment we've been looking at in our sleep GPA study and our vitamin C common cold study, right? We're taking our group of volunteers, we're partitioning them into groups that are receiving the explanatory variable at different levels, and then we're looking at the response variable coming out. So that's kind of the classic randomized comparative experiment. Another study, which is incredibly useful when it can be done, but is limited in how it can be conducted, is what's called a matched pair experiment. So in a matched pairs experiment, each case gets both treatments in random order, or cases get paired up in some other obvious way. We'll talk about that. And we examine individual differences in the response variable between the two treatments. Okay, now it would be helpful, I think, to have a concrete example to talk about so that we can kind of build a fence around these two ideas. All right? So imagine you're looking at two different types of poison ivy lotion, and you're trying to see which one gives better relief from poison ivy. Let's just say that the lotions are labeled A and B. All right. So design a randomized comparative experiment to answer this question, and design a matched pairs experiment to answer this question. So hopefully by the time we are finished looking at these two examples, we'll see the difference between these kinds of experiments. Okay. Now, in the classic randomized comparative experiment, we once again gather a volunteer group, and we're going to subject some of these participants to lotion A and some of these participants to lotion B. I should say ahead of time that what we've done is we've given them, let's say, poison ivy on both of their forearms. So these people are coming in, they've been infected, subjected to poison ivy. They've now got the poison ivy rash on their forearms. And now we're randomly assigning some of the volunteers to use lotion A and some of the volunteers to use lotion B. And then we're going to let that lotion take its effect, maybe over a period of 2 weeks. And then we're going to come back and see how did they do, how effective was lotion A in this group and how effective was lotion B in this group, and we'll compare their effectivenesses. Okay, so that's kind of the classic randomized comparative experiment. And as before, how we allocate the volunteers into groups A or B will be done randomly. We'll just use random.org, order the list, cut it in half, put one half in group A, one half in group B, all the usual things. We can conduct this experiment using a double-blind procedure as well. Okay, now, by comparison, what's a matched pairs experiment? What would be the version of this experiment in a matched pairs setting? So, once again, we collect a set of volunteers. We subject both of their arms to poison ivy. A rash develops. Now, what do we do instead? Well, we randomly pick one of their arms and we apply lotion A, and then we randomly pick, well, not randomly at this point, we take the other arm and put lotion B on it. We let that subject continue to use these lotions for a period of, let's say, 2 weeks again. And then what we do is we compare the effectiveness between lotion A and lotion B within the subject, okay? And then we aggregate all of these differences, right? We aggregate the differences between lotions A and lotions B throughout the entire set of volunteers. So rather than split the volunteers into two groups, one group gets A and one group gets B, we keep the group together as one large group, and we apply lotion A and lotion B within each individual, and then we're able to test the differences across individuals. Okay. Another classic way that these kinds of matched pairs experiments are done is when you can have a cohort and their twins. Okay, so we can have two groups. One and each group consists of pairs of twins, and then we can compare the twins with each other across these different treatments. And so it's not always the case that you can apply a treatment within an individual, but you can often apply different treatments across, let's say, pairs of twins. So now, most of the work we're going to do in this course is going to deal with randomized comparative experiments. That is the most common thing. We will touch on matched pairs experiments as we get near the end of the course. But it's important at this point just to understand that oftentimes we're interested in comparing two things, in this case, lotion A and lotion B. And there are two kind of ways that we could think of conducting this experiment: through randomized comparative methods or through matched pair methods. Okay, so that's that's a kind of a difference that we want to note at this point in the course, that there are different ways of conducting these experiments. Now, the last thing we want to touch on in this section is the use of randomness. And we'll see that there are two really important ways in which randomness are used in statistical studies, and we want to understand how these two methods are used and what effects these two methods of randomness have. All right, so let's move on to our next topic, the uses of randomness. So randomness gets used in two important ways in statistical studies. And we can really think about it by just exploring this little chart here. So a question we might ask ourselves is, was the sample randomly selected? So when you went into your population, did you draw out a sample randomly or not? Okay. Now let's look at the ramifications. Depending upon how we answer this question, we'll see how that affects our results, right? If the answer is yes, if you were very careful about randomly selecting your sample from the population, then it is possible to generalize from the sample to the population. So you can make that inferential leap from the sample to the population. But if the answer is no, if you didn't take proper care to randomly select your sample from the population, then you cannot generalize from the sample to the population. So you've lost part of the power of your experiment to make that inferential leap from the sample back to the population. So one way that randomness gets used is to pull the sample from the population. Okay. A second way is indicated by this question, right? Was the explanatory variable randomly assigned? So when you did your sleep study, or when you did your vitamin C study, how did you allocate your volunteers into the different sleep groups or the different vitamin C dosage groups? Okay, did you do it randomly or not? If the answer is yes, then it's possible to make conclusions about causality because you have washed out all of the other possible explanatory variables that are present, and you've now concentrated it on the one explanatory variable that you're concerned about. So you've created a range of values for the explanatory variable, and you've randomly allocated volunteers into those groups. So you can make conclusions about causality. If you did not randomly assign your volunteers to those groups, then you cannot make conclusions about causality. It just can't be done. You may have unwittingly introduced other possible explanatory variables into the situation, and therefore the response that you're seeing may not be a product of the one explanatory variable that you're interested in. Okay, so we have to be careful about using randomness in two different ways. One, in culling our sample from the population, and second, in assigning our volunteers into the different groups, okay, are the different levels of the explanatory variable. So be aware of these two very, very different uses of randomness and how they affect the study, okay? So that brings a conclusion to section 1.3, and that brings a conclusion to chapter 1. I will see you in the next video lecture when we jump into chapter 2 and we start in on section 2.1. I'll see you then. Until then, take care.